Hi, in this video, I will be talking about surds. In order to explain what surds are, I'm going to start from numbers. So I'm going to break down numbers, talk about the various types of numbers, then we'll talk about surds. So let's get started. I'm going to start from real numbers. Real numbers, real number is a set of real numbers are a set of all possible numbers you can ever imagine. So if you think about numbers from extremely large numbers, so let's say minus infinity up to plus infinity, we can think of any number within this range. They are all real numbers. There's another kind of number that is not real. We call those complex numbers, but they are beyond the scope of this video. They are beyond the scope of what we are to discuss today. And they are definitely outside the realm of secondary school or high school maths. So I'm going to focus on real numbers. Now we've got real numbers, which consist of set of all possible numbers you can ever think of aside complex numbers. Now real numbers are divided into two. We've got irrational numbers, irrational, irrational numbers, and we've got rational numbers. So what are irrational numbers? Irrational numbers are numbers that have special properties as follows. If you have a number with decimals that do not reoccur. So let's say you have a numbers like 1.1275136 and so on, such that you can't ever see any repetition in pattern. You call those kind of numbers irrational numbers. I'll talk more on them later, but let's talk about the rational numbers. Rational numbers are numbers that either they are whole numbers, that is, when you have either they are integers or numbers that you can express as a fraction of integers. So you call these rational numbers. So for example, if you have 0.333 and so on, you can express it as 1 over 3 because you can express this decimal as a fraction of two integers. You call this rational number. But let's break it down further. So rational number can be broken down into two. So you have fractions and you have integers. Integers, they are like whole numbers, but this time around they're both positive and negative whole numbers and zero. So integer consists of things you can call countable numbers like 1, 2, 3, 4. But this time around, it also includes negative number like -2, -3, -4, and so on. They are all integers. Then we have another class of number. So we have another class known as fraction, which is under rational. So a fractional number is, you can write it as a fraction as 2 over 5. This is a fractional number. Or you can write it as 0.4. This is a fraction. The key difference between a fraction and an irrational number is this. A fraction has either terminating decimals, in other words, like 0.25. This is a terminating decimal, right? So this is a fraction. This can be expressed as a fraction. Or if it has a decimal that does not terminate, for example, 0.17777, but this kind of non-terminating fraction has a pattern, has a repeating pattern. So this is also a fraction because you can convert this into a fraction of integers. But if the pattern is non-reoccurring, we can't see any pattern that is reoccurring, you call that a rational number. So this is a fraction because it has a pattern that is reoccurring or that terminates, or an integer that basically is like a whole number, a positive and negative whole number with zero. Now let's talk about um, integers. Integers can be broken down further into, we have negative integers. So we have negative integer. We have zero, and we have whole numbers. Whole numbers. Whole numbers can be seen as positive integers. So whole numbers can be, you can conceptualize as positive integers. So numbers, negative integers are like -1, -2, and so on. This is 0, then this is 1, 2, 3, and 4. So this is a kind of tree of numbers. So we've got real numbers broken down into rational number and irrational number and irrational number. Then rational number is broken down into fraction and integers. The integers broken down into negative integer, zero, and whole numbers. What about the irrational numbers? We can break this down into surds. So this is where we've got our surds. Surds and transcendental transcendental numbers. So let me spell it out clearly here. Transcendental numbers. So these are the two numbers that form irrational numbers. So what's the difference between a surd and a transcendental numbers? Surds are irrational numbers that emanate from roots. So if you say square root of 2, this is an irrational number, but it belongs to surd. If you say the cube root of, let's say, 5, this is also a form of, this is also surd. So you can imagine surd to be root of numbers. That's how you can imagine surd. They're just root of numbers. What about transcendental numbers? They are not, they don't result from the root of numbers. They result from some other kind of from other kind of special numbers. So an example of transcendental number is pi. Pi is approximately 3.14159265 and so on. You can't find any pattern in so. There is no recurring pattern in pi. So this is an irrational number, but then it's not an irrational number that is from a root of any number. There's a root of any integer. It's not a root of any integer. Then we have another transcendental number which is known as Euler, right? And the value is 2.7182818 and so on. So this is also an example of a transcendental number, and they are all irrational numbers. So today we'll be talking about surds. So this is what we're interested in. We're interested in roots of integers, roots of positive integers. So that's what a surd is. A surd is a number that is a root of, it could be square root, cube root, or whatever root of a positive integer. So let's get into it. So as stated earlier, a surd is a root of a positive integer. It could be a root, that's square root, or it could be a cube root, or it could be a fourth root. So it doesn't necessarily have to be square root, right? So this is a surd. But then in a surd, we are mostly interested in the positive value of whatever the result of that root is. The reason why I'm using the word positive is because if you take the root of 4, for instance, this is not a surd because if you take the square root of 4, you get 2. So this is not a surd. But let's look at this as an example. If you take the square root of 4, you either get 2 or you get minus 2. Any of this is valid because minus 2 times minus 2 will give you 4. Then 2 times 2 also give you 4. But in the case of surd, we are mostly interested in the positive results you get. So that's one thing you should take note of. Okay, so that is we've introduced sort. So now the next question is, what are the various types of sort? So let's talk about the various types of sort. So types of sort. Now we have pure sort. What are pure sort? They are sorts that consist of root of a single integer that cannot be broken down further. So these are pure sort, right? And you can't get the actual root of them. So these are pure sorts. Then we have mixed sorts. These are sorts that come alongside with whole numbers or integers multiplied to them. So if you have something like 3 root 2, for instance, this is an example of a mixed sort. This is the pure part and this is the integer part. So if you have another sort like 2 root 5, this is also an example of a mixed sort. And number 3, we have what we call like or similar sorts. If you say two sorts are alike, or if you say two sorts are similar, what you're saying is they have the same pure sorts. So what? Let me explain. If you have 2 root 3 and you have 3 root 3, because they have the same pure sort, you say they are like sorts or they are similar sorts. So because they have the same root sort, so you call this like sort. They may not have the same integer in front of them multiplied to them, but they have um, the same pure sort. Note that when you say something like 2 root 3, it's the same thing as 2 times root 3. So take note. So now let's talk about another type of sort. The fourth type of sort I'm going to talk about is binomial sort. Binomial sort. So what's a binomial sort? A binomial sort is a sort that consists of two. Bi means two, right? Bi means two. That consists of two sorts. So if you have a sort like 1 plus root 2, mind you, a binomial sort may not necessarily be made of two pure sorts. It could be made of, is a kind of composite sort that's maybe made of one integer plus another sort. But one of them must be a sort, right? Or it could also be made up of two different sorts, something like this. So this is also a binomial sort. As long as it has two components such that they are connected by plus or minus, you call that binomial sort. So this is also a binomial sort. If you have something like this, maybe 3 root 2, this is also a binomial sort. So these are binomial sort. They are made up of two parts connected by plus or minus. Now, binomial sort has something known as conjugate binomial sort. There's something known as conjugate. You can always get the conjugate of a binomial sort. So given a, a binomial sort of this kind, 1 plus root 2, the conjugate sort is the conjugate sort. This is not equality sign, so take note, they are not equal. The conjugate sort is 1 minus root 2. So the conjugate of a binomial sort is the sort that you get when you change the middle sign to the opposite. So if this is plus, you change to minus, then you get the conjugate. So what do you think this will become? Root 2 plus root 3. If you want to get the conjugate sort of this, it becomes root 2 minus root 3. So this gives you the conjugate sort. Now what about this other example? If you have 2 root 5 minus 3 root 2, the conjugate sort is 2 root 5. This is not equal to, just to show that the conjugate of this is as follows, plus 3 root 2. So you just change the sign and that gives you the conjugate surd. So this is how you get the conjugate surd of a binomial surd. Now we've highlighted all the types of surd. Now we'll look into the various the rules of surd. So let's talk about the rules of surd. Let's look at the rules of surd. The first rule is concerned with the addition or subtraction of surd. So if you have two surds of this kind, so let's say I have something like a root m plus b root m. Note that these are similar surds because they have the same pure surd, right? They are similar surd. If you have something like this, the result will be a plus b root m. It's like you are factorizing this root m. So you bring the root m out, then you add the the integer part of the surd. The rule also applies to minus. So if you have a root m minus b root m, then you say a minus b root m. So let's take a look at an example. So let's say you have a question like this. 2, let's say root 3 plus 5 root 3. This will give you 2 plus 5 root 3, and that will be 7 root 3. So this is the first rule. Let's take a look at the second rule. The second rule has to do with multiplication. Now, if you have roots n times n, that is, you have this, you can express it as root n times root n. So that's what this rule states. So let's take a look at an example. So let's say you have a surd like this, let's say you have a surd like this, root 20. You can write root 20 as root 4 times 5. And because you now have m and n, you can break it down further to root 4 times root 5. And now we can look for the root of 4, which is 2, right? Root 5. So this rule allows us to convert something that looks like a pure surd into a mixed surd. Because if you can break it further into this, you can take the root of each component and then simplify further. So that's what this rule states. So let's look at the third rule. The third rule has to do with division. If you have root m divided by n, that is everything inside the root, you can break it apart like this, root m over root n. So that is what this rule states. So let's take a look at an example. So let's say I have something like this, root 2 divided by root 3. I can represent as root 3, root 2 over root 3. So that's basically what the rule states. Now we look into a fourth concept, which is a concept known as rationalization. Rationalization of sorts. So let's break this grammar, rationalization. The word rationalization is came from the word rational, right? And in our starting, when we started this video, I spoke about rational numbers. So what rationalization of sort means is rationalization also involves you making the denominator of a given mixed or sort expression, making the denominator to be a rational number. So rationality of sort involves you making the denominator to be a rational number. So this is what it means. If you have a sort of this kind, because this sort has an irrational, it has an irrational number at the base. we say this is not rationalized. So when you're asked to rationalize the sort, what they expect you to do is to make root 3 to become a rational number. So basically, you are making the denominator a rational number. That's what rationalization of sort is all about, making the denominator a rational number. So let's look at how the rules guiding rationalization of sort. So let's take a look at this scenario. So if you have 2 root 2 over root 3, and you want to rationalize this, and you're asked to rationalize, right? Rationalize this sort. What are you going to do? For this kind of sort, you just multiply the numerator and the denominator by the denominator. So basically, what you're going to do is you're going to multiply both sides by the denominator. So this applies, so this is the general rule. The rule states that if I have root A, let's say over root B, and I want to rationalize this, what I should do is I should multiply both sides by, I should multiply both the upper and the lower region by root B. So that's what this rule states for this particular scenario. Even if you have mixed, let's say uh, you have mixed sorts like this, it's the same rule. You just multiply by just this pure sort. You won't multiply both sides by this coefficient, this value here, just the root b. So let's simplify this. So what this means is you multiply both sides by the denominator, and let's see what we get. If you do this, you're going to get root 2 times 3. If you apply the second rule, which says that you can break it apart and bring it together, what I mean by that is I can say root 2 times 3 is equal to root 2 times root 3. And I can also reverse the process. So I just reversed the process, I brought them back together. Then this is root 3 times 3, and this gives root 6 divided by root 9, which will give you root 6 over 3. Now there's something you need to understand, which is if you multiply sorts, two sorts, exactly the same sorts, right? Two pure sorts, the result is simply the number within this square root. So take note of this. If you multiply two square roots of this kind, the answer becomes this. So you don't need to multiply this to get 9. Just take one of the threes, and that gives you the answer. Now let's look at the second rationalization. If you have this kind of situation where, let's say you have a root b plus c, for instance. If you want to rationalize this, what you do in this case is you will multiply both sides by the conjugate of this. We talked about conjugate sort. So what that means is you will take this sort, you multiply by its conjugate, and its conjugate will be minus c. You just change the sign to get the conjugate. And whatever you multiply to the denominator, you multiply to the numerator. So this is how you rationalize this kind of sort. This kind of sort with binomial denominator. You multiply both sides by the conjugate sort of that binomial sort. Okay, so what do you get when you multiply two binomial sort? This is something you take note of. If you multiply two sorts, two binomial sort of which one is the conjugate, the short answer is always this value squared, then minus the other value squared. This idea came from the idea of completing the square, or the idea of algebraic processes where you have, if I have a squared minus b squared, I can express it as a plus b times a minus b. So it's the same concept here. Whatever you have here, you can just square this one with minus, and that gives you the answer. In fact, basically just square this, and that gives you b, then minus whatever you have here squared. So that's basically what you are going to get all the time. So now that we've talked about the rules of sorts, let's dive into simplification of sorts. And we're also going to solve a lot of questions as regards that. Now let's talk about simplification of sort. Whenever you are asked to simplify a sort, what they are asking you to do is uh, to break it into a smaller form or to rationalize it. So what that means is this: if I ask to simplify a sort, basically you're asked to apply all the rules that you can apply to make it more compact or to rationalize the denominator. So these are the two possible cases that could be implied whenever you are asked to simplify sort. So I'm going to demonstrate this with examples. So let's look at some examples from the UTME past question. Do note that this application I'm going to use is a software that enables students preparing for the UTME exam to prepare adequately for the exam. So it has thousands of past questions offline, and it has interesting features like educational games, question search, and so on. So I really recommend you get the application and you start using it to practice. We also have for other exams, like for the WAS exam and other major exams in West Africa. So let's get into it. So let's look at some past questions from JAMB. Okay, from the UTME app. I'm going to pick mathematics. Then I'm going to search for questions related to salt. The first question I'm going to solve is question number 7 from the year 2012. So let's take a look at this question. The question says we should simplify root 6 plus 2 squared minus root 6 minus 2 squared. Okay, so if you look at this question properly, you should notice a pattern here. There's this pattern of a squared minus b squared. If you check closely, you'll see that kind of pattern here. There's this pattern of a squared minus b squared. So we can use this concept that says the result of this operation is going to be a plus b, then into bracket, another bracket, a minus b. So we can apply that here. So we can say that root 6 plus 2 squared minus root 6 minus 2 squared can be equated to, take this to be a, take this to be b. So that becomes root 6 plus 2, then plus root 6 minus 2. Then you have another bracket, which is root 6 plus 2 minus root 6 minus 2. Now we open the bracket, we simplify here. So that gives us root 6 plus root 6. That will give us, if you apply the rule of addition, that will give us 2 root 6. Then plus 2, then minus 2. That cancels out. So that becomes 0. Now for this other case, we have root 6 minus root 6. If you open this bracket, that becomes minus root 6. That becomes 0. Then this becomes 2 minus minus 2. So minus times minus plus. So eventually you get 4. So if you multiply these two, you're going to get 2 times 4. That becomes 8 root 6. Note that when you multiply two things, of which one of them is a solid, you don't multiply the 4 to the pure solid, you multiply to the integer. So that's why we get 4, 8 root 6. And that means the right option is option C. The next question will be from 2015, question 11. So the question states that we should simplify root 147 minus 75 divided by root 48. So that's what this question is all about. So there's a root here. There's a root here as well. So this is the actual question. There's a little typo in the question. So now let's look at how to solve this. In this case, we need to rationalize this problem. So rationalize means we need to make this denominator to be an integer. So for one of the rules, what you just simply do is multiply both sides by this. So that means we're going to say 147 minus root 75, then times root 48, then we have root 48 times root 48. So this gives 1 root of 147 minus root 75 into bracket root 48 divided by 48. So the next phase of activity is to simplify this whole thing. So how can we break 147 into smaller parts? So if you think about it, what can we multiply together to get 147? Okay, the first is to determine if it is divisible by 3. And you can do that by just adding them up. If you add this up, you get 12, right? Since it's 12, it's divisible by 3. So if you divide this by 3, you are going to get 4. Then this will give you 7. This will give you 9. So you can say that 147 is 49 times 3. Now let's look at this one as well. 75 can be expressed as 25 times 3. And then 48 can be expressed as 3 times 16. So let's write everything in that format. So this 147 can be written as 49 times 3. This can be written as 25 times 3. And this can be written as 16 times 3. And everything divided by 48. So what next? Let's break this down so we can separate this 49 from this root 3. Then minus root 25 times root 3. Then this root 16 times root 3. So the next thing we can do is to simplify. So root 49 is 7. Then you have root 3 minus 5 root 3. Because root 25 is 5. Then everything 4 root 3 divided by 48. So the next phase is for us to break it down further. So which we're going to do in the next page. So let's bring what we have so far. That is 7 root 3 minus 5 root 3 into bracket 4 root 3 divided by 48. We can cut this. 4 here is 1 and here is 2, so that's 12. So we can make it simpler by breaking it down this way. Root 3, then root 3 over 12. So let's simplify what we have inside here. 7 root 3 minus 5 root 3 from the first rule. Since they have the same pure surd, you just subtract the number in front of them. So that becomes 2 roots. That's 7 minus 5, 2 root 3, then times root 3 divided by 12. So this will give you root 3 times root 3 will always give you 3. So that's 2 times 3 divided by 12. Then this gives you 6 over 12, and that gives you 1 over 2. So the answer is B, which is 1 over 2. So that is the solution to this problem. So let's look at the next question. The next question is question 44 from the year 2004. So the question states that we should simplify 1 over root 3 plus 2 in this form: a plus b root 3. Whenever I see a question like this, they just want to rationalize. That's basically what they want to do, such that you're going to get an integer here, you're going to get another integer here, and root 3. So let's see what to do here. To rationalize this, what we need to do is to multiply both sides by the conjugate of the denominator. So you multiply both sides by the conjugate of the denominator, which is minus. The conjugate is just to take this plus and change it to minus. So that's minus 2, right? So now, what do you do next? You want to simplify. Now, since we got 1 at the numerator, you just leave it as root 3 minus 2. So quickly solve problems of this kind. I gave a shortcut earlier. Don't break it down one after the other. Just know that whenever you multiply two conjugates, so just take the one with minus, square both sides, and that's all. So just square this and you're good. So just take root 3 square minus 2 square, and that gives you root 3 minus 2 divided by, if you square this, that will give you 3. If you square this, that will give you 4. And now you have root 3 minus 2 divided by minus 1. Now, if you take this, if you multiply both sides by minus 1, that is minus 1 times root 3 minus 2, then minus 1 times minus 1. That will give you minus root 3 plus 2. Then you can rearrange it as follows. You bring this to the front, then minus root 3. So what then is the value of A? So this is A. A is equal to 2. And B is an invisible minus 1. So B is minus 1. So that's what we've done successfully. So the answer is option D. So let's solve the last question, which is question 9 from year 2009. Question 9 from year 2009. We have 5 plus root 7 divided by 3 plus root 7. So to simplify this is to rationalize this, to make this denominator a rational number. And what that means is to multiply both sides, both the numerator and denominator, by the conjugate of the denominator. So what's the conjugate of the denominator? You just take exactly what you have here, but change the sign from positive to negative, and that gives you the conjugate. Then you do the same thing to the numerator. So that's 3 minus root 7, right? Now we can expand 3 times 5, that gives 15. 3 times minus 7, that gives minus 5. That's 3 times minus root 7, that's minus 5 root 7. Then root 7 times 3, that gives plus 3 root 7. Then root 7 times minus root 7, that gives minus root 7 square. And then you have the denominator here. So quickly solve for this. Since they are conjugate, just take the one with the negative sign, then square both parts. If you do this, you're going to get 15. Then simplify this. Minus 5 root 7 plus 3 root 7. What you simply do is you apply the first rule that says since they have the same pure surd, you just operate on the numbers in front of the surd. So minus 5 plus 3 will give you minus 2. Then you have your root 7. Then this will give you minus 7, because root 7 times root 7 will give you 7. Then divided by 9 minus 7. Then this will give, if you subtract this, 15 minus 7, that will give 8 minus 2 root 7 divided by 2. And if you divide both numbers by 2, if you spread this out this way, you're going to get 4 minus root 7. And that makes option B the right option. So this brings us to the end of surds. You can solve more questions by downloading this app, by downloading the Test Driller app, and by searching questions related to surd, and you'll be able to see a lot of questions related to surd, and you'll be able to gain mastery of this topic.